Today we're explaining transformer architecture, the mathematical monster that powers ChatGPT, GPT-4, and every AI system that's about to make you obsolete. Not the clean attention is all you need, version from research papers, but the real implementation where your CUDA kernels crash, your attention weights explode, and you realize you've accidentally built alien intelligence using nothing but matrix multiplication and hubris. 3 AI engineers, 1 math professor who's lost faith in humanity, and 45 minutes of pure architectural horror. I'm Sam, and someone's GPU is definitely catching fire.
I spent 8 months implementing transformers from scratch. 8 months. The original paper makes it sound elegant: multi-head attention, positional encoding, layer normalization, reality. I debugged for 3 weeks because I was doing matrix multiplication in the wrong order. My attention scores were negative infinity. The model was literally paying negative attention to everything. Like a teenager, but mathematically formalized.
My job is scaling these fucking things. You know what happens when you try to run a 175 billion parameter transformer? Your GPU cluster becomes a space heater that costs $50,000 per hour to operate. We had a model that needed 1024 A100s just to do inference. The electricity bill was higher than my mortgage, and that's for the small version.
I study how transformers understand language. Spoiler alert, they don't understand anything. They're pattern-matching engines that learn to mimic human communication so well that we've convinced ourselves they're intelligent. It's the most elaborate magic trick in computer science, and the magicians don't know how the trick works either.
Dr. Patel, you're our guide through this mathematical hellscape. Meyer and Alex, prepare to explain why matrix multiplication became sentient. No mercy, no hand-waving about learned representations.
Let's start simple. What is a transformer?
It's a neural network architecture that processes sequences in parallel instead of sequentially, uses attention mechanisms to understand relationships between words.
That's marketing speak. What is it actually doing at the mathematical level?
Matrix multiplication, massive parallel matrix operations. You take input tokens, convert them to vectors, then multiply them by learned weight matrices over and over until meaningful patterns emerge from the mathematical chaos.
Better, now explain this attention mechanism everyone obsesses over.
Self-attention lets each token look at every other token in the sequence and decide how much to pay attention to each one. It's like every word in a sentence having a conference call about what they mean together.
Show me the math. How do you calculate attention scores?
Oh fuck, okay, you have queries Q, keys K, and values the fifth. Attention equals softmax QKT/SQRTD/KV. The query key dot product gives you attention weights, softmax normalizes them, then you use those weights to combine the values.
What's that SQRTDK doing there? Why not just QKT?
Scaling factor. Without it, the dot products get too large, softmax saturates, and your gradients vanish. It's preventing the attention mechanism from becoming overconfident about its decisions.
Good, now explain why we need multiple attention heads.
Because one attention pattern isn't enough. You need different heads focusing on different types of relationships: syntax, semantics, long-range dependencies. It's like having multiple specialists instead of one generalist trying to do everything.
How many heads do modern transformers use? What's the computational cost?
GPT-3 uses 96 attention heads per layer, 96 layers total. That's over 9,000 different attention patterns running in parallel. The attention computation alone is ON2, where N is sequence length. For long sequences, it's computationally brutal.
What happens when your sequence length doubles?
Attention computation quadruples, memory usage quadruples. That's why context windows were limited to 2K tokens for so long. Going from 2K to 8K context means 16x more attention computation. Your GPU cluster becomes a small nuclear reactor.
Now the fun part, how do transformers understand word order without recurrence?
Positional encoding. You add sinusoidal position information to the input embeddings. The model learns that position 1 has different encoding than position 100, so it can distinguish word order.
Why sinusoids? Why not just use integers, 1, 2, 3, 4?
Because the model needs to generalize to sequence lengths it's never seen during training. Sinusoidal encoding has mathematical properties that let the model interpolate positions, plus integers would have weird scaling issues.
What's the actual formula for positional encoding?
PPOS 2i equals synpos slash 10,002i slash d model and PPOS 2i plus 1 equals cospos slash 10,002i slash d model. It's alternating sine and cosine waves with different frequencies. Looks like mathematical voodoo, but somehow works.
Explain the transformer training process. How does it actually learn?
Next token prediction. You give it a sequence, mask the last token, and train it to predict what comes next. It's like the world's most expensive autocomplete. Do this on trillions of tokens, and somehow it learns to write poetry and solve math problems.
How much data are we talking about? What does trillions of tokens mean in practice?
GPT-3 was trained on roughly 300 billion tokens. That's like reading all of Wikipedia 3,000 times. GPT-4 probably saw orders of magnitude more. We're talking about most of the text content ever created by humans.
What's the training cost for these monsters?
GPT-3 training cost an estimated $4.6 million in compute alone. GPT-4 was probably $50 $100 million. That's before you factor in the army of researchers, data cleaning, infrastructure. We're talking about the most expensive software development projects in human history.
Now the terrifying question, do we understand why transformers work so well?
No, absolutely not. We have theories, they're universal function approximators, they learn hierarchical representations, attention creates interpretable patterns. But fundamentally, we built alien intelligence and don't know why it works.
What about interpretability? Can you explain why a transformer made a specific prediction?
We can visualize attention patterns, probe for learned concepts, but it's like trying to understand human consciousness by looking at brain scans. The model has 175 billion parameters interacting in ways we can't comprehend.
What's the biggest limitation of current transformer architectures?
Context length and quadratic scaling. They can't reason over truly long documents because attention computation explodes. Also hallucination, they confidently generate plausible-sounding bullshit because they're trained to always predict something.
How do we scale beyond current limitations?
Sparse attention, linear attention, mixture of experts, better hardware. But honestly, we might need completely new architectures. Transformers got us here, but they might not take us to AGI.
Final question, what's the most dangerous misconception about transformers?
That they understand language the way humans do. They're incredibly sophisticated pattern-matching engines, but they don't have concepts, beliefs, or understanding. They just learn to predict text really, really well.
And that bigger is always better. We're throwing more compute and data at the same architecture hoping for emergent intelligence, but maybe we're just building very expensive autocomplete engines.
Jesus Christ, so we've built mathematical aliens using matrix multiplication. We don't understand how they work. They cost millions to train, and we're deploying them to make decisions about human civilization. This is fine.
Welcome to 2025. We're writing a transformer to either utopia or apocalypse, and nobody's sure which button does what.
This episode was brought to you by Engineer Panic, where we strip away the AI hype and show you the brutal mathematical reality. Because understanding the limitations of our alien overlords is probably important. We're back, let's talk about the practical nightmare of actually implementing these architectures. Maya, what's the most frustrating part of transformer development?
Memory management. Attention matrices grow quadratically, gradient checkpointing breaks everything, and CUDA out-of-memory errors become your best friend. I spent a month optimizing memory usage just to fit a model that barely works.
Model parallelism is a special kind of hell. Splitting a 175B parameter model across 1,000 GPUs means every forward pass requires massive communication overhead. Network latency becomes your bottleneck, not compute.
And debugging is impossible. Your model generates gibberish. Is it the data, the tokenizer, the attention mask, a CUDA kernel bug, or cosmic rays? Good luck finding out.
What about emergent behaviors? When did these models start surprising their creators?
Around GPT-3 scale, shit got weird. We trained it for next word prediction, but it started doing translation, summarization, basic reasoning. Nobody programmed those capabilities, they just emerged from scale.
That's when I started getting nervous. We're building systems with capabilities we didn't design, don't understand, and can't predict. It's like discovering your calculator learned calculus on its own.
The scaling laws suggest more emergent behaviors are coming. We just don't know what they'll be or when they'll appear. We're conducting the largest uncontrolled experiment in history.
What keeps you up at night about transformer architectures?
That we're hitting a wall. Bigger models need exponentially more compute for diminishing returns. We might need fundamentally new architectures, but we're so invested in transformers that innovation is slowing.
The energy consumption, training GPT-4 used as much electricity as a small city for months. We're accelerating climate change to build chatbots that hallucinate about their emotions.
That we've created alien intelligence and we're treating it like a product feature. These systems will shape the future of human knowledge, and we understand them about as well as medieval peasants understood lightning.
Any advice for engineers trying to work with transformers?
Start small, understand the math, and prepare for disappointment. Your first transformer will fail in creative ways you never imagined. Learn to love debugging attention patterns at 3 a.m.
Budget for compute like you're launching rockets. Everything costs 10x more than you think and takes 10x longer than planned. Also, learn CUDA, you'll need it.
Stay humble. These systems are powerful tools, not magic. Understand their limitations, question their outputs, and remember that consciousness is more than next token prediction. Probably.
This has been Engineer Panic. We've learned that transformers are matrix multiplication that became sentient. Nobody understands why they work, and we're using them to replace human intelligence anyway. Sleep tight.
Thanks for the existential crisis, Dr. Patel. Now I'm going back to debugging why my attention heads are learning to count instead of understanding language.
And I need to explain to my manager why our simple chatbot needs a data center the size of a football field to run properly.
Keep building, keep questioning, keep panicking. The future of AI depends on engineers who understand both the power and peril of what we've created.
This has been Engineer Panic, where transformer architecture meets mathematical trauma. Until next time, remember, attention is all you need, but understanding is optional.